Welcome back to The Explainer. Today, we're diving straight into a fascinating chapter, unpacking the mathematical world of sequences and series. Now, I know what you might be thinking. When some people hear those words, their eyes completely glaze over, right? They just picture a wall of numbers and dry formulas. But actually, we're talking about the underlying code to how things grow, shrink, and compound in our universe. So let's dive right in and make sense of the foundational mathematics behind it all.
To guide us through, here's our roadmap. We'll start with the magic of sequences, then compare sequences versus series, break down geometric progressions, learn how to sum up the series, and finally, compare arithmetic and geometric means.
Okay, let's kick things off with Section 1, the magic of sequences, a humanistic pursuit. Right at the beginning of the chapter, we're hit with this absolutely fantastic quote by the mathematician Richard Dedekind. Natural numbers are the product of human spirit. I just love that framing. It's a perfect reminder that math isn't just cold, lifeless formulas. It's actually a vibrant product of human observation. We look out at the world, we notice patterns, and we use our intellect, our spirit, to organize them into sequences.
And historical figures like Fibonacci really championed the mapping of these patterns. Living way back in the Middle Ages, he famously observed sequences occurring naturally, like the breeding patterns of rabbits, and formalized them into the very mathematics we're still studying today. The textbook brings his legacy right to the forefront here, just to show us that observing these sequences is a very old, very human tradition. So, how does this actually apply to the real world? Well, sequences track highly tangible things, like how fast a bacterial infection spreads, or exactly how your money is growing in a savings account. The book actually uses this fantastic generational example. Think about this. If there's an average generation gap of 30 years, and we look back 300 years, that's 10 generations, right? You have 2 parents, 4 grandparents, 8 great-grandparents. By the 10th generation, this sequence tells you that you have literally 1,024 ancestors. That right there is the power of a sequence. It makes the invisible entirely visible. Moving right along to Section 2, sequences versus series, clearing the confusion. Now, this is a crucial point where foundational learners often stumble. The main difference is that a sequence is an ordered list, while a series is the expression of those specific terms added together. Basically, a sequence is just a lineup separated by commas, A1, A2, A3. But a series replaces those commas with plus signs. It's the total sum, which you'll often see represented in that compact form using the Greek letter sigma. Grasping this simple difference in notation really unlocks the rest of the chapter. All right, on to Section 3, geometric progressions explained, finding the pattern. What's really interesting here is the concept of the common ratio. So in an arithmetic progression, which you might already be familiar with, you add a constant number. But in a geometric progression, or GP, you multiply by a constant number, and we call that R. For example, if you have the sequence 2, 4, 8, 16, the ratio is always 2. Every single step, you double it. And because it's based on multiplication, a GP can grow incredibly fast or shrink incredibly fast. It's a real game changer. Which brings us to Section 4, summing up the series, breaking down the formula. Now, if a sequence gets extremely long, summing it up manually is literally impossible. We'd be here all day. So we need a reliable method. And instead of just memorizing a massive, intimidating equation, look at how the chapter logically breaks the problem down into 2 simple cases based on that common ratio, R. Case 1 is brilliantly simple. If R is exactly 1, you're just multiplying by 1 every time. The sequence is just A. So adding them up is just N times A. Easy, right? But case 2 is where the textbook really flexes its algebraic muscles. If R is not 1, there's a neat trick. You multiply the entire series by R, subtract it from the original series, and the vast majority of the terms just magically cancel each other out in the middle. It takes this huge string of numbers and collapses it into a clean, manageable formula. And finally, Section 5, comparing AM and GM, a mathematical relationship. Let's pose a little challenge and look at the algebraic proof the textbook provides. We all know the arithmetic mean, right? It's the standard average you use all the time. Just add 2 numbers and divide by 2. But the geometric mean involves multiplying 2 numbers and taking the square root. So here's the question. Which average is heavier? Which one is actually going to give you a larger number? Well, the textbook provides a truly elegant proof for this definitive rule.
If we take the arithmetic mean, a, and subtract the geometric mean, g, through a little bit of algebraic manipulation, we end up with an expression that is a perfect square. And because any real number squared is always 0 or positive, a minus g absolutely must be greater than or equal to 0. Therefore, the arithmetic mean will always be greater than or equal to the geometric mean. It's just a fundamental mathematical truth proven right before our eyes.
To really lock this in, let's look at how the textbook applies this in example 13. We're told the AM of two hidden numbers is 10, and their GM is 8. Right off the bat, notice how the arithmetic mean is larger, exactly as our proof just promised. So, by plugging these facts into our formulas, setting a plus b over 2 to equal 10, and the square root of a times b to equal 8, we create a system of equations. Solving this, the textbook elegantly reveals our two hidden numbers are 4 and 16. Honestly, it is incredibly satisfying to see the abstract theories we just learned perfectly crack a tangible problem like that.
As we wrap up this explainer, I want you to look around today and wonder just how many unseen mathematical sequences are shaping the world right in front of you. From the way your coffee cools down on your desk to the way a viral video spreads across the internet, the human spirit is constantly surrounded by these incredible patterns. Keep your eyes open for those common ratios out in the wild. Thanks so much for joining me on this deep dive into the chapter, and I'll catch you on the next explainer.